need to waste your time as well. So good afternoon, good morning, good evening, everyone. It's my pleasure to welcome you all in the fourth lecture of this international lecture series of TC220 in field monitoring and geomechanics. And we have a very interesting lecture today from Dr. Ann. And personally, I really like that talk because she applied other things also based on her background on seismic data processing and also signal processing aspects. So we are very glad to, we thank you, Dr. Ann, for accepting our invitation to be a speaker for today's lecture. And with this, I would like to request Dr. George to say a few words of our activities of TC220.
Thank you very much, Neelima. Let me share my screen. You see my screen?
Yes.
Okay. So on behalf of the TC220 on field monitoring in geomechanics, and mainly on behalf of the chairman of this TC, Dr. Andrew Ridley, I welcome you all to this lecture, which is part of the activity that TC is developing in order to spread, let me say, the culture of monitoring around the world. Dr. Neelima is the organizer of this event, and we thank her very much for this effort. And we are sure that even today's lecture will be something which will provide us a lot of information and a lot of knowledge to add to our background. Just a few words regarding TC220, which has already been introduced by Neelima. TC220 is a technical committee of the International Society for Soil Mechanics and Geotechnical Engineering, and deals with field monitoring in geomechanics. Regarding field monitoring, or mainly the I&M instrumentation and monitoring activities, we want to remind some opportunities that those who are interested in can follow in the next future. Some of them are organized by the TC, some other not, but we want to mention them because could be a good opportunity for everybody. For example, in January, next January, we will have an interesting seminar or workshop organized during the TRB annual meeting in US, in Washington, DC, where people will discuss about a quite interesting topic, which is geotechnical modeling and monitoring when prediction and reality meet. We all know how difficult it is to predict something and how difficult it is to obtain something which is in agreement with the prediction, or vice versa, a prediction which are in agreement with the reality. So I think it will be a quite interesting chance for everybody to listen to something really interesting. Moreover, the British Geotechnical Association in February, 6th of February, will organize a mini symposium on the observational method. Again, something which is between theory and reality, as Elmo Di Biagio used to say. We have to meet, to join theory and reality by means of observation and monitoring. So it's another good opportunity to learn something more. The two events I presented are not organized by TC, whilst these two are organized, or better, in the frame of these two large events, TC is organizing a special event. The first one will be in Barcelona, in Spain, next year in June, from 17 to 24 June. And it will be, it will be a sort of, what is happening? It's a sort of mini symposium on field monitoring. It is organized by one TC member, Joseph Raventos, and it could be an interesting opportunity for discussing about field monitoring. Something similar, but a little bit larger in timing, is the event that has been organized, will be organized during the 18th European Conference on Soil Mechanics and Geotechnical Engineering, which will be in Lisbon, Portugal, in August 2024. And will be a full day organized by the TC220, discussing different topics related to field monitoring in geomechanics. And of course, the main event that we are looking for will be the 12th International Symposium on Field Monitoring in Geomechanics, which will be organized in India. Professor Neelima and I think even Dr. Singh will be are part of the organizing committee. It will be, if I'm not wrong, in September 2026, and it will be, of course, the most important events for field monitoring in geomechanics in the next years. It will be the 12th international symposium. This symposia started in the 80s, launched by Professor Kovari, Professor Sakurai, Elmo Di Biagio, and others, who later on organized different events in different areas of the world. So this will be the most important event, and I invite everybody to join this event, which will be for sure a great event because the organizing committee is doing a very, very hard work in order to have everything organized in the perfect way. But there are also other events, like the today events, which are organized under the umbrella of the TC, like the international lecture, like today, and the interactive technical talks, which have been launched by the International Society, which are talks where experts of different sectors meet and discuss in a very, let me say, informal way about some different topics. As you see, we have had a talk on field monitoring geomechanics, something on observational method. And if you go into the website of the International Society, you will find the list of all the events. TC has also a website. You can check the website in order to be informed and updated about all the events. As a LinkedIn page, which started quite recently and now has reached 440 and 54, let's say, almost 500 followers. And this is another way of following our activity, as well as a podcast, which can be followed and where a lot of information and a lot of talk are recorded or can be listened in order to understand what is going on in our field of activity. So this is very quickly what I want to remind you. This lecture, as all the other, are recorded on the YouTube channel of the International Society. So you can find all these events and you can review them whenever you want. By this, I thank everybody for attending this event, and I leave the word to Neelima and her colleagues. Thank you very much.
Thank you, Dr. George, for updating the TC220 activities. So with this, I'd request Dr. Anil Joseph, President, Indian Geotechnical Society, and also TC220 member, to say a few words.
Yeah, good afternoon all, and it's been a great pleasure to me to be part of this TC220 series as a member of the TC220 committee. And it's a big, every month we have as a curtain raiser for the ISFMG 2026, we have started. Congratulations, Neelima, for doing all the hard work and getting the right people on the job. Today we have Anne with us talking on a very interesting topic. Thank you, Anne, for joining us for this program. And we have Giorgio with us, who had given a briefing of what all we are doing in TC220. It's a very important and vital aspect with the artificial intelligence and machine learning coming in, the field monitoring, geomechanics, and the observation method has to make a disruptive change to bring in safety in the construction, and also optimization in the construction is possible. And as they simply say that unless and until you measure, you cannot manage. So the measurement of the aspect is the vital aspect. As field monitoring and geomechanics people, we are doing it. We are doing it on a tricky situation of a very element which varies horizontally as well as vertically. And we have to be very vigilant with our thought process, and the sharing of knowledge with eminent speakers is possible. And a very, very interesting topic today. And we are all eagerly waiting to listen to you. I don't want to take much time. I thank everyone who has joined in this program. And in fact, this is a chain which is being published in the YouTube also of our TC220, and make sure that it reaches maximum people so that the important knowledge is shared to the mass public, so that we come up with better geotechnical engineering. Thank you all. Thank you very much. And all the best for this thing. And once again, I congratulate Neelima for doing an excellent job.
Thank you, Dr. Anil. So without wasting any time, I would like to introduce a speaker. Before going to that, I'd like to inform to all the participants, maybe some of you may already aware, we have a YouTube channel of TC220 and also LinkedIn page. So I suggest you to follow that so that you will get the monthly updates, and a lot of activities are happening, and field monitoring is such an important area in the coming future. So that is one thing. Along with that, we also have a YouTube channel of Indian Geotechnical Society. So please do follow that, because every month we have so many activities by different chapters, because we have almost 52 chapters as of now, if I'm correct. So we are a large body of almost 6,000 active members of the country. So I request others also just to follow so that you can get updated. With this brief words, like it's my pleasure to introduce Dr. Ann to the all the participants today. Dr. Ann, thank you so much again. So she has a background in acoustic imaging and digital signal processing from University of Oslo, with a BSc degree in computer science, followed by MSc and PhD in signal processing. She has many years of working experience, including seismic data processing and analysis, sonar signal processing, vibration monitoring, large structures, as well as, in design, installation, instrumentation systems. She has been employed in the instrumentation and live monitoring section at the NGI for the past 10 years, where her responsibilities included coordinating, practicing actively in different R&D projects, as well as consulting work in the installation and instrumentation for different offshore projects. So her main primary research focus in the recent years has been on marine monitoring related to offshore. So with this brief introduction, over to you, Anne. So you have 45 minutes and your lecture is recording, and so followed by 15 minutes question and answers.
Okay. Thank you very much for the kind introductions, everyone, and for the opportunity to speak today. I'm really happy to be here. It's a very interesting forum for me. Let me see if I can share my screen here. Okay. So I hope you all can hear me and see my screen. Please let me know if you can't.
Perfect.
Yeah.
Okay, very good. So the topic for the lecture or talk today is offshore monitoring and assessment of leakage at the seabed, with focus on the second part, so assessment of leakage. I'll give a little bit of examples into the first part as well. So as was mentioned, I work at NGI, the Norwegian Geotechnical Institute. And for those of you who are maybe not so familiar with us, we are mainly based in Norway. We have our headquarters here. We do have a few scattered offices other places in the world. We are an independent foundation. We work internationally within a broad range of topics within the geosciences. And we do a good mix of consultancy and R&D work. As of now, I think we're about 380 employees. We might, that number might be a little bit higher, actually, continuously growing. So the work that we do at NGI can be roughly divided into 4 market areas. We have offshore energy, predominantly within wind at the moment. We have natural hazard, geodata and technology, and geotechnics and environment. And I belong personally to the geodata and technology group within the section of instrumentation and live monitoring. Yeah, so the rough agenda for today's talk, I'll give a few examples from the work we do on offshore structural monitoring at NGI. It's not what I personally work most on, but it is a major activity for NGI as a whole. And there's, of course, overlap between those activities and the work that I do as well. And then I'll move into the topic, the main topic for today, which is detecting and assessing seabed leakage, which is a quite broad topic, actually. So I'll try to define a little bit what we mean by leakage or seepage. So it can be called one or the other, depending on the application, where it comes from. I'll present some key applications where monitoring is important to detect seepage and leakage and to try and characterize what it is. And then I'll present some of the recent and ongoing R&D activities that we have here at NGI. And finally, I'll point a little bit towards future trends within both R&D and commercial applications. So starting with a few examples from the offshore instrumentation section at NGI of major projects that we've been involved in over the recent years. So structural health monitoring here to the left is a major application. And NGI's specialty in actually all of these applications is in developing and designing custom-made sort of fit-for-purpose monitoring solutions, where we use, most of the time, we use off-the-shelf available technologies, but we then integrate them into a complete monitoring system. So this is an example to the left. I wonder if I had a laser. There we go. To the left is an example from structural health monitoring from offshore wind, where we have a suction bucket foundation that's heavily instrumented in this case with the strain gauges, inclinometers, accelerometers, and more, from the buckets up, including the jacket, all the way up to the transition piece. And the data from all of these sensors has been collected into a DAQ system and sort of visualized to the operators. And this is important to both to monitor loads, both wave and wind loads that the structure is subjected to, and of course to measure the dynamic response of the structure, and to say something about its life expectancy. We are often also involved in installation monitoring and guidance, where a structure is instrumented so that the operators can ensure a safe and controlled installation at the seabed and penetration into the ground. Final example to the left here is another activity that we often are involved in, which is large-scale model testing. This is an example from offshore Taiwan with axial pile load testing. Beneath is also an example from axial pile load testing, but in that case, actually from the onshore market related to infrastructure. And we do have a dedicated section for offshore instrumentation monitoring. The head of section is Stephen Hayes. So if you're curious, feel free to contact him. Another example, a very interesting one I find, is retrofit installation of monitoring solutions, where you have some structure offshore and you want to install sensors that were not placed there when the structure was installed. So this is an example from a project we had. It took place off the east coast of the US. And the task was to install accelerometers on the structure, retrofitted, so using, in this case, magnetic fixtures. Okay, so that was just a brief sort of a peek at some of the offshore monitoring of structures that we do at NGI. And now I'll move on to the main topic of this talk, which is detecting and assessing seabed leakage or seepage. So NGI actually has quite a long history of monitoring leakages at the seabed for different applications and using different technologies. So this is an example from 2005, where NGI was involved in qualification of a methane gas sniffer, or chemical sensor, to detect methane leaks. Later in 2012, NGI was involved in a commercial project where the task was to develop a leak detection and monitoring system to be placed below an offshore structure to detect the leaks from the seabed. And I'll say a few words more about this later in the talk. Later again, NGI coordinated a quite large R&D project called ACT for Storage. Stands for Acoustic and Chemical Technologies for Environmental Monitoring of Carbon Capture and Storage. This was a very sort of applied project with a lot of field measurements, and I'll show quite a lot of examples from that project today. We certainly learned a lot from it, so I hope it might be interesting for others as well. Currently, we have an ongoing project looking at automated detection, because one of the main challenges in seep detection, as in many other applications, is the immense amount of data that you end up with and the amount of manual labor needed to look through everything. So automated detection is really sort of up and coming. And I'll also show an example of an ongoing research project, which is a follow-up project of this earlier Act for Storage project, but focusing on autonomous underwater vehicles and how we can make them more efficient platforms for marine monitoring by making them more autonomous or able to act according to their environment in real time. Okay, so what do we really mean by seabed leakage or seepage? Well, it can be many different things, and not everything needs to be monitored, but some aspects are quite important to monitor. So this is an example of natural seepage where methane is seeping into the marine environment. That's very common in many places of the world. It's probably always been there. It's visible in the water column as bubble streams locally and sometimes sporadically occurring. In some cases, it results in pockmarks at the seabed. There may be features on the seabed indicating that there has been or is fluid flow, and there may be a chemical sort of plume that's measurable, detectable in the water column. So why is this important to monitor? Well, methane is a greenhouse gas. And as a greenhouse gas, it's much more potent than, for example, CO2, although that's also, of course, an important greenhouse gas to consider. Natural seepage of methane has always been occurring, but today there is a lot of CH4 methane trapped in permafrost in the ocean, sort of below in the sediments. And as ocean temperatures rise, this sort of is released. So we can have an increase in the amount of methane in the water, and then we can start to get a spiraling effect where you have methane entering the atmosphere, increasing global warming, and then more is released. So this needs to be monitored to understand the global carbon cycle. The challenge here is, of course, that the oceans are vast, and we don't know exactly where these leaks occur. So it's a little bit like looking for a needle in a haystack. But luckily, it's a very loud needle. So bubbles in water are acoustically very, very strong targets and very easily detected if you are there. But the challenge lies in the large search space. So you would either have to be lucky and be at the right place at the right time, or you have to have very comprehensive monitoring strategies. So another application or kind of seepage is what we would call leaks from infrastructure at the seabed. So we have oil and gas pipelines at the seabed, a large amount of these and growing amount. We also have where there has been oil and gas production and wells have been shut down. They are capped, closed and abandoned. This is an example from BP. Modern wells are usually capped in a very good way, but there are also many legacy wells that are maybe not as well closed. You also have the opportunity that natural gas may use this as a conduit or a path to find its way to the seabed. Here's an example where methane is leaking up outside the casing of a well. And this adds up to a considerable amount of gas, and especially the oil and gas operators are being pushed by governments to have control over this. So this is the Nord Stream 1 and 2 gas pipelines, if you remember, quite recently, and those are not the challenge. Those are easily detected using other means. Medium-sized leaks, for example, from pipelines, are generally not so challenging to detect either, because there are mass balance systems that will detect these as there will be a drop in pressure. But it's the small leaks that may be left undetected over time. And that can cause significant both economical loss, and it can also have an environmental impact. And finally, there may be leaks, natural leaks, but near infrastructure that can pose a safety hazard. So I'll show another example from a project we had at NGI a few years back, where that was exactly the case. This is an offshore structure in the North Sea. There's an issue with natural methane seeping up near the platform. And the concern is that this may cause a loss in stability of the structure. So it needs to be monitored. So I'll jump back. The solution that NGI provided at that time was to place 6 monitoring nodes beneath the platform. These are equipped with a combination of acoustic and chemical sensors. So acoustic sensors to detect the bubbles, and chemical sensors to characterize the leak. Here's some example images of sonar images from one of the nodes. The node is placed in the middle like this, and it forms a 360-degree image where you can see the structure. It looks a little bit funny because sonar images tend to map 3D structures down to 2 dimensions. But within this very sort of loud image, you have a small leak out here. And with some filtering, it's possible to detect that and to issue an alarm to the operators. This is what one of the nodes looked like before installation. Okay, so moving on to another application is CCS, or carbon capture and storage. And the concept of CCS, it's been ongoing in Norway for some time, since I think 1995, but it's really picking up speed now. The concept is that CO2 is captured either from industrial sources, such as fertilizer production and cement production, but also through oil and gas production. It's captured, it's then transported either through pipelines or by ship out to some location offshore. Can also be onshore, but we're focusing here on offshore. the offshore case, and then it's injected through a well down to some suitable geological formation, typically either a saline aquifer or a depleted oil and gas reservoir. And the aim is to reduce greenhouse gas emissions. But of course, you need to make sure that the injected CO2 stays in place. That is expected. There are no indications as of now to considerable leakage, but the operators are there are regulatory requirements to the operators that they have to confirm that this is the case. And this is a little bit similar. It's very similar to the natural seepage case, where you have the pipelines and you have the wells that are quite easy and obvious risk structures, but you also have a vast area that you might need to cover because you don't know exactly where there might be a fault that you don't know about, and you may have leakage. So moving on to the aquifer storage project, which is aimed toward the application of CCS specifically. And the problem or the challenge that this project wanted to address is that, yes, we know that bubbles are detectable acoustically, and that chemical plumes can be characterized chemically, but there are so many different sensors available on the market and so many different technologies, types of acoustic sensors in particular, it's very difficult to come up with a good monitoring plan. We need to understand the capabilities and limitations of the different sensors much better. So here are some of the sensors that we used in this project, which is we used a representative range of available technologies. So when it comes to acoustic sensors, we used a multi-beam that you would typically have on the mounted beneath a vessel. It's very good at mapping the seabed. It has a very good area coverage rate, but it's not so good at quantifying the leak rate. We then used a scientific echo sounder, which is designed for the fish industry, and it's used to estimate the abundance of different species of fish. It's very sensitive. As an example, where you see the seabed and you see a small leak. This is from our controlled release experiment, but it can also be used to acoustically quantify the leak. We used a smaller imaging sonar, which is a little bit similar to the one used in the previous example beneath the platform. It makes an image, an acoustic image. So here's an image from this sonar showing a subsea structure. I think it's a part of a bridge, but it can also be used to detect leaks. And then you have passive acoustic systems, because bubbles, when they're emitted from the seabed, they make noise, and they make a very characteristic noise. So that can be sort of a low power, low cost sensor that's useful in some applications. But how do you know which sensor to use when? That's one of the questions we looked into. And then also, what are the implications of taking these sensors and placing them on an autonomous underwater vehicle, for example, for better area coverage rate? How do they work then, and what considerations do you need to take into account? We have chemical sensors. In this project, we used a lot of them, but the obvious ones are CO2, methane, and pH and oxygen sensors are very useful. The key difference between acoustic and chemical sensors is, of course, that acoustic sensors are remote sensors, so they can detect leakage at a distance, but they can't say anything about which type of gas it is. But chemical sensors, they're point sensors. They need to be in the plume. But they can tell you something about. They can tell you what type of gas you have. But another important factor to look into is, okay, what happens when you take a chemical sensor that has a response time and put it on a moving platform such as an AUV? That has an important impact, and I'll show you the results shortly. I'll skip that one. So because this is we're interested in measurements here, field monitoring, I'll show you some of what we did during the controlled release experiments in this project. So this is Norway. We had the experiment here in the Oslo fjord. It's very convenient for us, but it's not too far off from the North Sea. It's the same water masses, and the conditions are, for the sake of this experiment, this project, quite representative of the North Sea. We had a DIQ system at onshore with pipes and cables out to both a leak frame where we had controlled release of CO2, but also 2 sensor platforms that we instrumented with a number of acoustic and chemical and oceanographic sensors. This is from the site. So we injected, this is the release point here, about 100 meters from shore. We released both CO2 in gas phase, but also dissolved in seawater. That's what we use those tanks for. And here's the CO2 in gas phase that we saturated the seawater with before releasing, so we could release both pure CO2 bubbles, but also seawater from selected depths at the area saturated with CO2, and measure the plume acoustically and chemically. This is set up. We designed and built a very simple release frame for releasing CO2 at the seabed. And we had 2 sensor frames equipped with chemical sensors, current meters. It's very important to understand the ocean currents when you're measuring this, at least when you're trying to interpret the data that you get, but also acoustic sensors. So here, a scanning sonar, same one that was used in the monitoring system beneath in a structure offshore, the M3 imaging sonar that I showed, and 2 echo sounder transducers. And we also had a hydrophone. This is what this frame looks like in practice, with the M3 sonar here, the imaging sonar with bathymetric capabilities, and 2 different EK80 scientific echo sounder transducers with different frequencies. We also built a subsea container to hold the electronics that we needed for these experiments. So quite an extensive experimental setup. Okay. So let me show you some results from the stationary sensor template, which was placed 25 meters from the leak, that was equipped with the chemical and oceanographic sensors. And chemical sensors are, as I mentioned before, they're point sensors, so they're not able to detect leakage at a distance, but they can still be useful for detection if you place them in the correct location and near some risk structure, such as a well. And one of the interesting findings that we had was that the extremely good high degree of correlation between oxygen and CO2 when you don't have a leak. If you see, the CO2 is the blue line here. Each plot shows a 12-hour interval of data, and the red line is oxygen. And as you can see, these mirror each other very, very well. And this is because these 2 parameters, they co-vary naturally. And if you plot them, you can also see that they have a very nice linear relationship. But when we release CO2, we observe anomalies. And if you were to look at only the CO2 or only the oxygen, you wouldn't really be able to say anything. But by looking at the correlation between these parameters, you are able to detect anomalies that then indicate that there's a secondary source of CO2 in the area. But when using chemical sensors, you have to be put a lot of thought into where you place these sensors. You have to, of course, take ocean currents into account, but also the buoyancy of the plume. CO2 mixed with seawater tends to become heavier than the surrounding waters and sink, while as methane is the opposite. You have to really, really plan this well to measure something. Okay, so let me move on to, that was one example from the chemical sensor frame, which was placed stationary at the seabed. But of course, when you're monitoring these vast ocean areas, you can't place stationary sensors or frames all over the place. You need to have moving vehicles. So we looked at what can you use an autonomous underwater vehicle for, how well is that able to detect and assess a leak. We used a surface vessel. This one was from Kongsberg Maritime, equipped with all of their acoustic, sort of state-of-the-art acoustic equipment. And we used a glider, which is also an AUV, also an autonomous underwater vehicle, but designed for operating over large periods of time. So it's very power efficient. It doesn't have a propeller. It uses buoyancy control and wings to control its movement in the water. And what we did here in the Hugin, for example, is Hugin is the name of the AUV. We took the same sensors that we had on the stationary platforms and put them into the AUV to isolate the effects of measuring with something that's moving through the water, not stationary at a single point. So firstly, looking at the acoustic data that we acquired using this research vessel, the Simrad Echo. Not so surprising. Here's this. I don't know if you've seen multi-beam images before, but if not, the sea surface is up here, and you look out in a fan-shaped sort of area. You see the seabed, and you can see the seep. And this is when releasing 1.3 liters of gas. I'll show you a little video so you can get a feeling of how what kind of a size of leak that is. So bubbles are detectable acoustically. We knew that. But what was very interesting, and here's an example of where predictions do not match observations, is that we observed them very high into the water column. Here from the seabed, 35, sometimes 40 meters above the seabed consistently. And predictions say that CO2 bubbles are completely dissolved within at least 10 meters, no more than 10 meters above the seabed. So that was an interesting observation, and we've looked into that and have a hypothesis that there's some gas exchange going on, that the predictions or the simulations are not able to sort of to include all of the processes you have in nature. But for monitoring, this is a very good thing because it's much easier to detect something that has more of a vertical extent. Let me see if I can. This is the leak. We didn't have this is an R&D project, so limited budget and a bad camera, but you can at least see what the leak looks like at 60 meters depth. There are other interesting properties of bubbles that you can investigate acoustically that can tell you something about the nature of the leak and the size of the leak. And one of those parameters is the frequency dependent information. Here are some examples of the seep, the same seep as on the previous slide, insonified with a transducer at different frequencies from 18 to 200 kilohertz. We use this information to acoustically quantify the leak, and the preliminary results are pretty good. We want to do a new experiment next summer to verify and to look more in detail into this. But of course, acoustic quantification has a huge advantage when you're covering a large area, because then you can actually quantify a leak as you pass it with a vessel. You don't have to go there and place some instrument there to do a direct measurements. Okay, I'll go a little bit quickly through the past slides here because I think you want to finish Q2. I'm correct. So let's look a little bit at the acoustic sensors and what they observe when you're insonifying the leak at the seabed from an AUV using its side scan sonar. In this case, it's a synthetic aperture sonar, which is a very specialized side scan sonar aimed at really high resolution images of the seabed. So this is an image of the area with no release, and you can see our sensor frame here. You can see the release frame. There's no release at this time. You can see cables on the seabed and rocks and other features. to really get a good impression of the seabed. This, we were unlucky with the image quality, so it's really bad, but you can see that how strong even quite a small seep is in the image. So really is a powerful technology for detection. Yeah, here's the instrument frame and the leak frame. And then looking at the chemical data, how does that look like when you go through this plume a number of times? Can we measure it chemically? So starting with the CO2 data, this is a 3D cube of the area where the Hugin AUV traveled. The leak is down here, but it's not detectable. We can't see it. And that's because the chemical sensors have a response time. It takes a while for them to react. And because the vehicle moves through the plume is small, it doesn't measure anything. However, the pH sensor, because if you have an increase in CO2 in the water column, that also reduces the pH, and the pH sensor is a much faster sensor. So the takeaway message from this is if you're measuring a plume using an AUV chemically, use the fastest possible sensor, so a pH, not a CO2. Okay, so what we learned from this project and other sort of parallel ongoing projects at that time was that the technologies are there. We can detect this and we can measure it, but it's still very cumbersome. It's time consuming to monitor large areas. It's expensive, and the amount of data produced is often overwhelming. So to address this, we believe that a higher degree of autonomy and automatic processing is key. So current R&D is largely directed towards making AUVs more autonomous, providing unmanned surface vessels, or vessels replacing the surface, the big research vessels with small unmanned ones, and automated detection and analysis. So why autonomy? This is a normal survey vessel. Now this small sail buoy is on the market. It can carry an EK80 transducer. So one of the main sensors that would you use for mapping on this. So the crew here is 50 persons. Here you don't need any persons, and you get the same data. We're not quite there, but this is the direction. And this, of course, reduces the CO2 footprint and saves costs and time and reduces risk. Let's see. Sorry, I went the wrong direction. There. Yeah, and then there are other larger unmanned surface vessels that can carry more advanced sensors. And we're currently looking into automated processing, and we hope to test that in a field trial this summer. So a current project that we have, I'll just give you a few examples from this since we're running out of time, but it's a follow-up project of the Aquifer Storage project, but focusing on AUVs. Because we did see that AUVs were certainly a very powerful tool for monitoring large areas and detecting and characterizing seepage, but they're not efficient enough. They have navigational autonomy, but they lack situational awareness. So they don't use their sensors in real time to act based on their environments. They collect data and then they come back. So what we're trying to look into is, can the AUV use its sensor data in real time to sense and act based on this information, and then due to this, provide more useful information. So we have an ongoing project on this using these two AUVs. To illustrate what we're after, this is the way these AUVs are used today. You define a pre-programmed travel path that the AUV follows. If you encounter a plume, you may completely miss it. You may not actually go through the plume. And if you do go through it, you have very limited data from this feature of interest. And then you have to go back and revisit the area. So what we want to achieve is something more like this, where the AUV uses its sensors in real time to detect that it's encountered something of interest, and then to acquire more data here, enough data to be able to characterize this. So you don't have to go back and remap it. But this requires a lot. It requires situational awareness within the AUV in real time. And that again requires that the sensors on the AUV are able to automatically detect a feature of interest and feed this information into the navigational system of the AUV. But we are working on it. We have a project where we aim to address this. And I think I will, because I'm running out of time, I will skip past this. But we have an ongoing project now, and the aim is to do exactly this, to implement automatic detection using the acoustic sensors on the Hugin AUV, and maybe also on the Eloom AUV, and to have that processing integrated and running on the onboard PC, and to also feed that into a real-time model of the surroundings that will then allow the AUV to act, hopefully intelligently, based on this information. So our ambition is to demonstrate a new level of autonomy using these AUVs in the Oslo fjord with a similar controlled release of CO2 as the one we had previously. So this is planned for, the first field trials are planned in June 2024. Okay, thank you very much. And I'm happy to take questions or discussions.
Thank you, Dr. Ann. It's an interesting topic. So it's open, floor is open for any questions or anything.
May I?
Yeah, please, please.
It's not a question, but just a consideration. First of all, of course, thank you, Anne, for this very, very interesting presentation. It is always fascinating to see what can be done underwater. Many times we are in trouble just to install an instrument on the into the ground, and it is really nice to see what you are able to do underwater. And this leads me to another consideration, that is that underwater or offshore instrumentation is a sort of edge limit or edge situation which provide our community a lot of opportunity to understand what can be done. I mean, you are using a lot of technologies, you are using a lot of sensor instrument, and from them we can derive something to use in different applications. So I think that offshore could be considered as the driving area for instrumentation and monitoring, because you are dealing with very complicated problems, and you are working in a very, very challenging environment. And this is something very useful. And I know that the NGI has always been the reference for the offshore monitoring. And so I hope that all the research that you are developing will be in the next future available for everybody to solve even other problems. I'm thinking about, for example, about a dam project, where you have to deal with the reservoir, to know what is happening underwater the reservoir, starting from the sedimentation to many other parameters, like chemical parameters or presence of leakage or presence of gases and so on. So starting from offshore, we can derive technologies and solutions even for onshore applications. So again, thank you very much, Anne, for this interesting presentation, and good luck for your research.
Thank you very much.
Dr. Ann, there is a question in the chat box. So someone is asking, like, can we detect leakage? I think pipeline leakage. Oil leakage. Yeah, pipeline detection in the seabed, I guess. Can we detect the oil leakage?
Can we detect the oil? Oh, that's a very good question and very interesting one. Yes, oil droplets. It depends on the case basically. But if you have a small oil leak, you will typically have droplets, and that's detectable acoustically because you have a change in acoustic impedance. You don't have nearly the same change in acoustic impedance as you have between oil and gas, or sorry, between water and gas. So if you have a bubble, that's much stronger acoustic target than a droplet in water. But yes, it is detectable. And a colleague of mine, not at NGI, but he was employed as a postdoc for a while. He's now at Kongsberg, I believe. He's looked specifically into that acoustic quantification of oil droplets. Mm. So yes, it's difficult, but it's possible.
So there is one more question, Dr. Ann. You can see the chat box, otherwise I will read that. Whether marine conditions will change after tsunami or earthquake, how can be monitored?
Yes, that's a very good question. And this is where maybe two topics meet. I don't know so much about what would change, but certainly acoustic methods, they can detect leakage, but they were originally designed for seabed mapping, at least some of these. So mapping the seabed and looking at the bathymetry, looking at how the seabed has changed, that's certainly possible acoustically. Also looking into if you have a change in the sediment properties, that can to a certain extent be mapped acoustically. So if those are the kind of changes you're interested in, then yes. And of course, also if you see, sorry.
Sorry to interrupt, but unfortunately, I have to leave. I apologize for this. Again, thank you very much, and thank you, Neelima, for organizing this lecture, and hope to meet you again for the next lecture. Thank you very much. Sorry.
Thank you.
Thank you, Dr. George.
If we detect the gas leakage in seabed, so enjoy. That's a good question. If we have a method to stop the leakage, that's not something that at least I have been involved in my research. Mainly, we would monitor, we would provide advice and quantify the emissions. I'm sure something could be made to stop the leakage, but depending on what it is, it's often a matter of, if it's a pipeline, of course, shutting the pipeline down and repairing it. So not something typically NGI would do.
Okay, so thank you so much, Dr. Ann. And so if there are any more questions, please feel free to contact Dr. Ann in future also. So we can provide the details of the speaker. So with that, we will close this session. So I thank again, my sincere thanks to Dr. Ann for such an interesting topic. I really like that topic because it is having highly multidisciplinary and much ahead of the time, I can say. So thank you so much for sharing your work, and hope to see you in 2026 at IIT Indore. So I'd like to invite you and all everyone to just follow us in our LinkedIn and of course YouTube pages for other updates. So you can register. Once you register, you get the monthly lecture series details and other updates also from TC220 and the Indian Geotechnical Society. So with this, I'd like to close this session. So if there is nothing, thank you so much again. So see you.
Thank you very much.
Thank you.